to talk to you about KinExA data analysis, interpretation, and skepticism of your data and interpretation both. Models and options I'm going to touch on today include the one-to-one equilibrium binding model, the bivalent cooperative constant binding partner binding model, the equilibrium three-way competition binding model, the choice of reference, the use of drift correction, the use of titrant-related NSB, ignoring data, and how KinExA confidence intervals are calculated and why I prefer them to mean plus and minus 2 standard deviations. So my first case study has to do with ignoring data points and drift. I'm going to Alt-tab out to the KinExA Pro here, where I have this example live on my screen. So this is an N-curve analysis, and I'm highlighted curve 2 here. And if we look at the binding signals tab, the instrument tab, then this is the trace in question. It's kind of delayed onset. It's got some kind of little funny bump in it, and then it looks kind of misshapen here. It does join up with the group of curves in the slow rinse part, and for most of the fast rinse, although it looks a little funny here too, at least if it's the same trace. The color appears to be the same. And we can confirm that and look at the curve in detail by going to the additional data tab. And I want to see which curve it is. I want to confirm that that is the same, that one where it's off on the lower end a little bit. So I click over here in the binding signal, and when I do that, it highlights the corresponding trace on the graph. And then I can step down through it with the arrow keys, and each trace lights in turn. And when I get to this trace, I can see it clearly. And it definitely is the same trace that looks like it's pretty low in here. It's the lowest one in this elbow, and it's right near the bottom of the group on this end as well. And the other thing I look at here is I notice that there is a pressure anomaly. I'm going to zoom in here. So I'm clicking on Shift and then holding down the Shift key and clicking and dragging my mouse. When I do that, it zooms in on that portion of the curve. And this is the pressure trace. And the pressure is negative because the KinExA system operates on suction. We're pulling the sample through and then the label. And so I'd like to confirm where this is starting, so I can grab my cursor up here in this window. And once we get to 150 seconds, it will appear in the lower window as well. And I can see that this is definitely starting right at 150 seconds. And I've already reviewed the timing setup for this experiment. And so the first 120 seconds was sample, then there's 30 seconds of buffer at the same flow rate, and then we switch to label at the same flow rate. So as soon as we switch to label, we see that the pressure has dropped down away from the rest of the group. And I can use the arrow keys here. I can go up 1 or 2 or 3, and then I can come back and I can go down 2 or 3. And yeah, they're all in a group right there, except this one. And this one looks pretty odd. So it's a lower pressure. That means there's some kind of obstruction to the flow. And it starts when we introduce the label, but it ends at 270 seconds, you can see here. And this is buffer again. It's flowed at the same rate as the label, which is 1/4 mil per minute in this case. And then we switch to a faster wash rate, and the pressure anomaly continues through both of those washes. So something's impeding the flow. And one possibility for this is bubbles. There could be bubbles in the bead pack. So I come over here and I look at the bead pack. I look for bubbles. I do not see any. This is in the after sample image here. This is just a slice of the bead pack, so it's possible there are bubbles in here that we don't see, but I'm looking for some rationale for rejecting this trace, and this is not providing it. The picture here is not. But we have 2 points against it. It has a weird looking fluorescence trace, and also something happened in the flow, and it's unique to this trace out of this entire experiment. The rest of the pressure traces are reproducible. This one's different. That affects the flow. We can't predict exactly what's happening here, but the flow is not the same if the pressure is different here. There was restriction. And then the third thing I notice is over here in the binding signals, this one is negative, and none of these others are negative. So everything's positive except this one. So that's 3 points against this thing and in favor of we can ignore it. There's one more thing I like to do. First, I'll go to the binding signals tab here. And this already ignored here. I'm going to unignore it. Whoops. And then I'm going to go back out to the N-curve analysis. So these analysis results were obtained with that point ignored. And in that case, I'm getting 3.2 nanomolar and 5.25% error. When I look at the error graphs, I see we've resolved both of these between the KDs between 1.2 and 6.4 nanomolar, and it's between 27 and 70 nanomolar for the active CBP. This looks pretty good. So now what I want to do, this is with the data point ignored, but I've unignored it. So I'm going to click reanalyze, and I want to see how this changes. So when I reanalyze that without that point, okay, this has shifted from 3.2 to 3.8. The confidence interval has shifted a bit too. It's from 1.5 to 7.8. And this is from 23 to 71. So these numbers have not changed significantly. We are easily including most of the range of the other analysis, and the other KD is included in our confidence interval, and the same here is true for the active CBP. So ignoring that data point didn't significantly change the analysis results. And that's the most important thing that I look for when I'm thinking about ignoring a data point. I don't want it to change my analysis dramatically. If it does, that means that your whole analysis is sensitive and really ultimately based on one data point. If that's happening, I don't want to use either ignored or not ignored in that case. I want a different experiment where I'm not relying on a single data point, where my fit is spread, the importance of the fit is spread across the curve instead of relying on a single point or even just a small handful of points. So this looks okay to me. I'm going to go ahead, I'm going to go back in to here. I'm going to find that negative point, 0.14. I'm going to ignore it. I'm going to come back out to here. I'm going to click Analyze, look at my binding curve. Okay. This looks okay, but I'm still not real happy with the fit. I see there's quite a bit of variation in these curves. And so I wonder if drift would help. And the drift correction, which is selected here for each curve individually, and it relies on monotonic drift model. So jumping into curve 2 here again, what I mean by monotonic is I mean that the change is occurring in the same direction. So most, if not all, of the change in these data points needs to be, for example, downward or upward. If every other data point, if this point looks like it's drifted down and this one up and this one down and this one up, then that's not going to, drift can't fix that. Drift is to a model that accounts for a monotonic drift. It's the sig 100 is drifting down by a certain amount per run, and or the NSB is drifting by a certain number of millivolts per run. And in this case, these lower points look very well reproduced. I'm wondering about the monotonicity. So I can click on this point, and it highlights the point, and it highlights over here in the binding signals column. And then I can use the arrow key to step up. When I do, it highlights the next point, and 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 the next point. And since these were run, there's the first run of 0 through 187 picomolar, and then we start over with 0 through 187 picomolar. And so all of these second points are in the second trial. So that's what I consider monotonic data. And then on the rest of these points, whoops, that's an up arrow key. On the rest of these points, when we look at them, they're basically on top of each other, except this last point. And we've already decided to ignore that point. So I'm not too worried about it. Actually, that's the first point. Yeah, no, that's the second point on this concentration. So this is a good candidate for drift. I'm going to turn drift on for this one. And then I'm going to go take a look at curve 1. And I'm going to do the same thing here. I'm just going to click there, and then I'm going to up arrow through these. I'm looking to see, are they all, the second one's lower? And they are, until this one is higher, and then these two are basically on top of each other. So we have 1 out of 12 or 14 here, 12 it looks like, where 1 of 12 where it is in the opposite direction. Okay, that's still reasonable. We'll still be able to get an improved fit from the drift correction. It'll make a compromise on this point some. It's not going to be able to fix every point, but it can still help here. And I feel okay about turning it on since the large majority of data is monotonic. So I'm going to turn it on there too. And then when I go back out to here and click reanalyze, let's see, let's look at the error curve before we do. Before I click analyze, I'm going to come back here to the error curves. And here I see it's 3.16 nanomolar, 1.2 to 6.4, and 46 nanomolar, 27 to 70. And now I'm going to click analyze with the drift correction turned on and look at how these change. And so this has not changed at all. It's changed by 0.01 nanomolar, but the confidence interval has narrowed up. It's from 2.5 to 4 now. And here, this is not changed, but it's narrowed up. And this is what I expect from drift correction. I expect it to narrow up the confidence interval, which happens because it's dramatically improving the fit of the data. But again, I don't expect this to change the KD or the constant binding, the CBP activity significantly. If it does, I wouldn't trust it. If you can turn on drift and it changes your values significantly, that alone is a reason not to use it. And you should look deeper into your data to understand what's going on. Okay, so let's go back to our presentation here and advance to the next slide. So I have another case study. This one's model shopping versus repetition. So I'll go back out to the end curve here and open this up. So this is data that was measured at Sapedine, and it was given to me to review the results. And when I look at this data, something jumps out at me immediately. I'm pretty picky about my data fit, and I expect my data my model to fit the data very well, and that any residual error between the best fit theory and the data to be random. And when I look at this low curve here, and I imagine an average of these two data points, I see this one's low, this one's low, this one's low, this one's high, 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 low, low, and high. And that, to me, does not look random. It looks kind of like periodic. It looks almost, it could be sinusoidal. It's high, it's low, it's high, it's low, it's high. So, I don't trust this. And another way to say that is the data looks like it's too steep for the theory. You can see, if you imagine connecting these points, the midpoint of all these together, that the curve is going to be steeper than the theory curve here. But so the data is steeper than the theory curve in this case. So I know one thing that can fix that is the cooperativity model. So I can just go ahead and click on it and try it, because that's really easy to do. And when I run this with when I analyze this with cooperativity, yeah, that fits a lot better. The error has been reduced. And let's look at the error curves and see, it's actually resolved the Hill coefficient even. Hill coefficient of 1 would be non-cooperative. So if this confidence interval included 1, I would reject use of this analysis on that basis, but that doesn't apply here. It's resolved between 1.3 and 1.8. Okay, so the problem here is that the customer for this data is adamant that it's a monovalent system. Both the constant binding partner and the titrant are monovalent, and cooperativity is a multivalent model. You can have cooperativity as long as you have more than one binding epitope. You can, if you have 2 or 3 or 4 or 5, any number really, you can have cooperativity. But in KinExA, our cooperative model is limited to a valency of 2 cooperativity. So you cannot fit trivalent cooperative data here, but you can fit bivalent. but you can't fit monovalent because monovalent cannot exhibit cooperativity. So this model is simply wrong. And that's true even though it provides an excellent fit to the data and everything seems to be resolved well when we look here. We just don't trust these results because we know the system's monovalent. We know this model's inappropriate. The fact that your model fits your data does not make it the right model. So I'm going to go back here to the equilibrium binding model. No, I'm going to go back to the equilibrium binding model. And I want to reanalyze that now so we can take a look at it again. Okay, here it is. All right, so that's not it. It's not cooperativity. All right, what else could it be? Well, one other thing that I know of that can make the data look too steep for the analysis is if there's an error in the CBP concentration. And one thing I like to think about, I like to look at the Sig 100 and how it scales with the flow rate and concentration. And I might do this in my head, but I've made a little table here to help us out so I can explain it to you so we can all understand it and be on the same page. So I expect the Sig 100 to scale with the CBP concentration. If I put in 10 times as much CBP, I expect 10 times more signal. When I look here between curve 1 and curve 2, curve 1 was at 1180 picomolar, curve 2 was at 118. So curve 2 I would expect to be, other things being equal, I expect to have 1/10 as much signal from curve 2. Okay, but then I also expect the Sig 100 to scale with the sample volume. And the sample volume went up from 50 to 500, so that's a factor of 10. So that cancels this out. And the flow rate is the same, and that's really just a check here. If the flow rate is different, the Sig 100 doesn't necessarily scale with the flow rate. So this is a trick that really I only use if the flow rate is the same for both curves. And that's common, luckily, but it's not always the case. So you do need to keep that in mind. So here I'm expecting the Sig 100 to be the same, factor of 1 between curve 1 and curve 2. When I look at the actual fitted and measured Sig 100, it's a factor of 1.5 higher on curve 2. All right, this is not a super big number. It's not super definitive, but I already have another reason to suspect something might be going on in this curve, the steepness problem. So this heightens my suspicion. I'm going to go back out to the KinExA Pro here. What I'm going to do next is I'm just going to change this. I'm going to say, all right, this has been specified as 118 picomolar. I'm going to go into timing setup. I'm going to change it. I'm going to double it to 236 because in my experience, if there is an error, it's usually an even number. You know, you were supposed to draw 2 microliters, but you only drew 1, that kind of thing. So I'm going to assume it's doubled and click that through. And then I'm going to go back out to here and I'm going to analyze it. Now we have 2.4%, 74 picomolar here. And it lowers it dramatically, it improves the fit dramatically, and it changed the KD quite a bit. Now here, I'm not so worried about changing the KD. If there's a concentration error, then that really does affect the KD, and if you fix it, you're going to change it. I'm not worried about the significance of the change in the KD. I expect the error to go down if I'm helping it, and it has gone down, and that is reflected in the visually better fit here as well. Okay. So I'm suspecting this concentration error. I go back to the scientist who got this data and we review his notebook together, and I'm happy to say it was very clear and easy to follow, and it definitely laid out his calculations and they looked right, and it laid out his volumes of pipetting and all that added up and appeared to be correct. There was nothing in the notebook to support the hypothesis that this is an incorrect concentration. All right, in this case, I'm going to ask for a repeat. So that's what I did. I asked him to run this 118 picomolar curve again. And I'm going to ignore that one. And I'm going to unignore this one. And when we do that, okay, we get back a curve that fits a lot better. I do not see any troubling systematic. This looks like it's plausibly random noise to me. Nothing jumps out at me as, oh, that looks periodic or anything like that. So I feel pretty good about this. This is the data that I'll be happy to report. Now, if I change the concentration on this, which I did, I haven't changed it back. And with that changed, I could put that curve on there and it should all fit, and it does. But I'm not going to report this curve because I don't have any documentation to support the change in concentration. I think that's what happened, but that's not enough for me to include this in a report or to publish it. So this data is left out. This data we're just not going to use. So I'm ignoring it here. And this is what I will report. Okay, there's one more thing I want to milk out of this example, and it has to do with the drift correction. So I'm going to unignore that curve. I'm going to ignore this curve. And then I'm going to go into curve 2. I'm going to change this back to 118. And then I'm going to go into the binding signals tab, and I'm going to ignore the second trial. Now, I already warned you that you cannot use the drift correction if you only have singlet data. And now I'm going to go ahead and do that to show you the one of the numerous reasons why you shouldn't do this. So when I do that, if I come back out here to the analysis and I click Analyze again, okay, we still see the same thing. Low, 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 high, 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 low, low, and high. So I still see the same problematic look of a problem here. And when I look at the error curves, it still says it's resolved. It's between 47 and 108 picomolar here. So now when I turn on drift correction for this second curve and click Analyze again, it takes it a little while to do it because it's thinking, it's exploring some territory here. But it comes back and says, hey, I've done it. And now it's between 13 and 29. Now, I warned you already that if you see a case where you significantly change the KD, you ought to not trust it. This is that case. And how does it do that? Well, when we come out here and look at it, it has really improved the fit. It really has. It doesn't, I mean, there's still, 2 below. These are 2, maybe 3 above, 3 below, but these are a lot closer to the line. And this is the kind of thing that might pass. It's shifted the shape of this line to make it fit the data better. It's lowered the error, and it's done that by changing the drift or the SIG 100 level by 0.79 per run and the NSB by 15 millivolts per run. These are pretty significant changes. And it's been able to do that and change the shape of the curve. And that's because the drift model is pretty powerful, can have a pretty big effect on the curve shape if it's not constrained by duplicate or more data. And so the problem here is that I didn't have my duplicate data here. I can't really use it appropriately. So this is just an additional warning to you. And also to keep an eye on your values. This one did change significantly. So that right there should be a red flag to you to not use this drift correction. And you already ignored the first red flag of, oh my God, it's not duplicate data. All right, back to the presentation. And my next case study, that's an invalid use of drift correction. That's what I just showed you. Drift correction requires replicate data. Use of drift correction with singlet data is never valid and may be misleading. Yes, that's what we just saw. Okay, I have another example here, titrant-related NSB, and this one is in the KinExA Pro. Here we are. So this is what we look for titrant-related, if we want to try titrant-related NSB. We look for a curve that has come down to we expect to be a lower plateau, but then starts to increase. And what we're modeling here is we're saying, well, the titrant itself can have non-specific binding to the solid phase. And when we get down to the lower plateau, we've bound all the antibody to titrant. So if the titrant sticks to the solid phase, it will drag a bound antibody with it, and it can then be labeled in the subsequent step and raise the signal level. And that can happen, we expect that to scale with concentration. So the titrant-related NSB model replaces the constant NSB with a constant plus a term that is proportional to the titrant concentration. So I'm just going to turn it on here and see, does it help? I guess before I click Analyze, I'll take a look here. We have not resolved the KD, but it's below 1.2 picomolar. We have resolved the CBP here, and it looks pretty good. So let's go ahead and click Analyze. And we still have not resolved that, but we have resolved this. It still looks good. When we go back now to the binding curve, it really flattens that out, and it still fits well here. So this is appropriate use of titrant-related NSB. And we can leave that on. This looks like it might be a candidate for drift correction too. We can go back into the binding signals and take a look at it. Click on that point and barrow across this. And the second points, every single one of them is low. This is definitely a strong candidate for drift correction. So I can go back into the binding curve and I can turn on drift correction 2 and reanalyze it. And that's a nice fit. We're down to 1% error. This is fitting very, very well. And the error curves, we still can't resolve the KD. This is a very high ratio curve, but it's below 405 femtomolar now, and the activity is very well resolved, very sharp and nice. I just realized that I skipped something in one of the earlier examples. I'm going to go back and pick it up. And that was in this very first one, I think. Yeah. There's a problem here. Maybe some of you picked it up and I glossed right over it. Now, the problem is that, yeah, it says it's resolved the CBP activity between 38 and 50 nanomolar, but that's 3,728% above the nominal CBP. That's 37 times higher active CBP than there is total CBP in this system. And that's a red flag. I just reject that out of hand. I don't believe. It's easy for me to wave my hands and say, okay, you haven't done as good a job of purifying as you think, or some of your protein is misfolded. It's all there, okay, but not all of it's active. So I can accept pretty much any number less than 100%, but numbers that are greater than 100%, especially numbers where the confidence intervals are well over 100%, 320, so at least 320-fold extra. No, I just don't believe it. Or 32-fold extra. No, I just don't think that's right. And the way that I address it is I change my reference. So I come over here, we've been referencing the titrant. I change to the constant partner. I click Analyze again. And now this curve is 2.8% activity. So the titrant is very low activity. And I can accept this. That's a small number, but I've seen a lot of numbers this small and smaller. So I don't have any problem accepting a low activity on the titrant, but I do have a problem accepting a very high titrant or a very high activity on the CBP. And the KD has changed significantly here, and that's because it's tied to the reference. And so we've shifted it 37-fold tighter as well. It's 85 picomolar instead of 3 nanomolar now. But I believe these numbers are more defensible, and this is the numbers that I would want to report on this system. Okay, I'm going to go back to our presentation. We've gone through the titrant-related NSB. Okay, the next model I want to talk about is the competition three-way. This is a model where we assume that the constant binding partner is a mixture of two or three different KD bindings. So they recognize the titrant, but there's two populations or three that recognize the titrant with differing KDs. And these curves here are from a 2003 publication from the Omura lab where they mixed antibodies. So here's antibody A and antibody B, and the solid line is the mixture of antibody A plus B. And you get this funny inflection point in the data. And if you have A and B that are farther apart in the KD space, then when you mix it, you can get this big step in the middle of it where it's basically flat. And it can look a little steep even. Up here, it's the same thing. It's A and B mixed together. And it makes the curves look pretty funny. Okay, so again, I have a case study that we can go through on this. And it looks like this. This is some in-house work we did. We were measuring an anti-insulin antibody binding to a biotinylated insulin. And on the high curve here, you can see that it looks pretty funny. It looks kind of well, it seems to be drifting, still drifting down, but it's drifting down very slowly. So the first thing we wondered is it even real? Let's reproduce it and try to extend it a bit. So we did that. And when we do, yeah, it reproduces pretty well. And it looks like maybe eventually it is reaching a plateau out here. Okay, so this kind of funny curve shape can be the result of a mixture of CBP. And we have a model for that. So I'm going to go ahead and try it on this data and see how it works. It's the competition three-way model. Whoops, not the concentration immunoassay, but the competition three-way model. And when I apply that model and click reanalyze, it takes a minute, but it comes back, and yeah, that really fits the data much better. It ties all this data together in a very pleasing way. Now, does this mean that there's really a mixture here? Well, no. I don't think this is sufficient evidence. The fact that the model fits the data is really never proves that it's the right model. But models that don't fit the data, you can usually it's because it's the wrong model choice, although it might be an experimental error like what we saw in the first example here. So, you have to be careful. And choosing the model is a big deal. Now, here, I would love to go to print, for example, and say there's a mixture of this somehow, but I'm going to want some additional evidence before I do that. There's one piece of additional evidence that I have here that I can kind of bend to my theory, and that is that this is an antibody measured against a biotinylated insulin, as I said, and we measured this same antibody against a non-biotinylated insulin, and it looked perfectly normal. So my hypothesis here is that there's a part of the population of the antibody that is recognizing the linker to the biotin with a different KD. And so it looks like we're binding, it looks like we have two populations of binders here. But I wouldn't go to print in that. I'd want more data. I'd want supporting data, maybe mass-based data. I'd want something to tie this down in an orthogonal method before I put this out as a publication. And by the way, by default, the competition three-way only fits for 2 KDs. So here it's saying the model that fits this data has a first KD of 766 picomolar, and that comprises 78% of the total CBP. And then there's a population of 21% or 22% that binds with a much weaker 105 nanomolar KD. And that corresponds to this flat part down here. Okay, let's go back to our presentation. And I believe that is the end of the case studies. Now I want to talk to you about error graphs. So this blue line is a KinExA error graph that I've exported and replotted here. And now I've annotated it. So I want to tell you what this error graph is showing us. So we're doing a least squares analysis. We're fitting our theory to the data set. We're doing that by varying the sig 100, the NSB, the constant binding partner, and the KD. And we find the set of those 4 parameters to give the minimum error. And that minimum error is this right here. It's a best fit error percentage here. This one is about, looks like 6%. So this is a pretty noisy curve. And the best fit KD is between 1 and 10 picomolar here. And so this point is a point on my error curve. The best fit point appears on the error curve. And this is a KD error curve. So as we move away in the KD axis, I've gone out here to 10 picomolar and I've set the KD to 10 picomolar and I haven't varied it. I've held it fixed at 10 picomolar and I've varied the other 3 parameters to find out what's the best fit I can get at a KD of 10 picomolar. And I've recorded that noise as this point right here. It's a little bit higher than the best fit as it should be. This is the best. There shouldn't be anything lower than that on either side in this error graph. And then, so we've just done that. The way this curve is constructed is we've just gone along, we've fixed the KD at a bunch of different values out here, and we've reoptimized the other parameters, and we've recorded the error and plotted it here. And we keep repeating that until we reach a threshold. This error has increased by a certain factor of this one. And when we get that, we stop. That's far enough. Or when we go in the other direction here, we're hoping that it's going to cross and we're going to stop at a factor, but in this case it doesn't. And when we get about 300-fold below the best fit error in KD, so this is the best fit was, I don't know, 5 or 6 picomolar here probably. And so we've gone down to 2 or 3 femtomolar here, or sorry, 20 or 30 femtomolar here. And that's far enough. That's 277 or 300-fold below the best fit. So the error, we quit looking. We say this is too flat. Okay, so now to compute the confidence intervals, we take the best fit error, the minimum error, and we multiply it by a scaling factor, and we plot the scaled error as a horizontal line shown by this dashed line. And then we look for where that intersects the error graph. It intersects right here. So the KD corresponding to that intersection here, that's, I don't know, 20 or 30 nanomolar, or that's 20 or 30 picomolar, is going to be the upper limit on the KD, on the confidence interval. On this end, that graph, that scaled error graph, doesn't intersect the scaled error doesn't intersect the error graph. So we're going to say the CI is unbounded on this end. Okay, so this is how we do it in KinExA. It's a scaled error approach. Now that's compared to something like a plus and minus 2 standard deviation. Now, I'm sure this looks familiar to you. We have a Gaussian or bell curve. And for a bell curve or a normally distributed curve, if you have a normally distributed random variable, 95% of the values will be within 2 standard deviations of the mean. And that's shown here by these dashed lines, 2 standard deviations at 95%. All right, so can we apply this to KinExA? Let's talk about it. So first off, we need to recognize that the 2 standard deviations is for a population. If you know your whole population and you know it's normally distributed, then you can use 2. But if you have a small number, and according to this website I looked up, that small number is less than 30, then you really ought to be using the t-distribution. The t-distribution does converge with the standard normal for large numbers, large degrees of freedom, and the degrees of freedom is related to the number of points you measure. So if you have a degrees of freedom of 2, your curve is considerably lower in the middle than the standard normal curve shown here in red and brown, and it's bigger, it's fatter, we say, on the tails. And to include 95%, you're going to have to go a little farther than 2 standard deviations for your degrees of freedom 2 curve. And I did this for n equals 3, where we're measuring the KD 3 times in 3 separate experiments. We're not doing triplicate. We're preparing the solutions 3 times. We're running them through the KinExA. We're measuring 3 separate KDs, and then we're averaging them together, calculating a standard deviation. And then we're going to try a plus and minus. And so I looked up the formula, and if we have n of 3, then using the t-distribution, we should be adding plus and minus 2.48 standard deviations. Okay, so now let's look at the distributions that we have. So this is simulation here. I simulated 1,000 Sig 100 levels and added a Gaussian distributed random noise to each one. And this is my histogram of those 1,000 values. And overlaid on top of it is the best fit standard deviation, best fit normal curve based on the mean and standard deviation of the data set. And that looks plausibly normal to me. As I fill in a bunch more points, I can kind of imagine that this might converge on some random normal bell-shaped curve. Okay, and the other thing I did is I used the Shapiro-Wilks test, which is a test of normality. What it does is calculate the probability that your data could be as far from, your population could be normal, and your data could be as far from normal as the data that you're presenting in the test. What's the probability that that could happen? And it's 0.83, so it's quite high. This data looks normal. Okay, so this is 1,000 Sig 100s, but I also calculated 1,000 at 11 other data points with different titrant concentrations to create 1,000 curves, simulated curves. Each individual data point got its own random noise estimate. And then I ran those 1,000 simulated noisy curves through the KinExA Pro analysis, and I recorded the KD values. And that's what I'm showing here, 1,000 KD values from simulated noisy data. And I'm showing the best fit mean and best fit normal curve based on the mean and standard deviation. And it looks like a poor fit. This data does not look normal. For one thing, the KD can't go below 0, but this curve wants to. I've just cut it off here. And the data has points way out here. It looks like there's quite a bit of data. I mean, not a majority of it, but there's a significant number of points out here at very large values, and that's not a normal distribution. And, it's kind of peaky here. It just doesn't appear normal. And the Shapiro-Wilks formalizes that by telling me that there's a 0% chance. The probability is 0 that this came from a normally distributed KD. So the KDs are not normally distributed. So that's telling us that we really shouldn't use the mean plus and minus 2.48 standard deviation. But we know that in many cases, you can get away with it. For one thing, there's the central limit theorem. And so when we take 3 points and we average them, those averages should be eventually normally distributed. That's the beauty of the central limit theorem. So, I want to try it. So I went back to my simulations and I chose 3 of them. And I analyzed them in the KinExA Pro, each one by itself. And in each case, it said KD low was unresolved. And then I analyzed the 3 of them together as an N curve, and it said the KD is unresolved. And then I took the average of my 3 reported KDs and the standard deviation, and it says the KD is resolved. So I can easily appreciate that it's far more desirable to report the KD's 4 picomolar between 1.8 and 6.5 than it is to say the KD's 4 picomolar and it's less than 32. I much prefer to report the narrow range, but is it really fair to do so? So the next thing I looked at was, let's try it for a lot of these things. So I simulated more data, and what I'm showing here is tables. This first row is the noise. So I simulated from 0.5% to 8.5% noise. And then I looked at different ratios, a ratio from 1 to a ratio of 32. And here in this lower graph, this is the KinExA Pro CI. So this is just the confidence interval that's reported. And I went back and I looked at how many of the confidence intervals reported in the KinExA Pro included the true value, which I know in this case because it's simulation. The true value here is 4 picomolar. So I went back and saw how many of the confidence intervals include 4 picomolar, and that's what I'm recording here for each noise and ratio combination. Each of these each of these points represents 1,000 simulations in this table. And you can see here that it's running between 93 and 100%. The average, which I haven't shown here, is about 95 or 96%. It's right in there. I think this is a pretty good estimate of a 95% confidence interval. But I did the same thing for the 3-point standard deviation confidence interval. And here I had the same 1,000 results. I sampled them 3 times randomly, and I did that 1,000 times. So I went back and I got 3 random samples 1,000 times out of my 1,000 data points. And then I calculated the mean and standard deviation and a confidence interval from that. And I asked the question, how many of those confidence intervals include the true value of 4 picomolar? And the answer is, again, it's basically 95%. Again, it's a variable. It's 93. It goes up to 97. But yeah, these average out to be 95%. This looks really good. So even though I don't feel like it ought to be working, it's working. So let's go one step further, though. So on those high curves, those high ratio curves, I think a majority of those curves should be not resolving. In fact, I wonder if any of them ought to resolve. A ratio of 32 is getting up there. Should we really be resolving a KD out of that? So I asked the question, how many are unresolved? And for the plus and minus 2.48 standard deviation, I said it's unresolved if the lower bound went below 0. And in that case, we had 70% here at the noisiest, highest ratio. But at the noisiest, lowest ratio, we still had 12% unresolved. Now, in the KinExA method, the scaled error method that we use in KinExA, at 82% of these were unresolved, but only 2% of the low ratio. Now, this is a KD-controlled curve, and even in noisy data, I do expect to resolve quite a few of them, perhaps fairly broadly, but I expect to resolve them. And KinExA says, yeah, you've resolved 98%. The 3-point standard deviation is 88%. Which one's right? That's an interpretation, but in my opinion, this is better. So I'm more comfortable with this. And then the other thing I want to do is I want to go back one more time to this error graph. So here I've redrawn the error graph from the previous slide, and I've overlaid the confidence intervals. This dark blue band is the plus and minus 2.48 standard deviations confidence interval, and this light blue band is the KinExA confidence interval. It's around 30 picomolar on this end, and then it goes all the way down. It goes to 10 femtomolar and below. So it shades all the way down on the KD axis. And I went back in and I looked at the best fit at each of the confidence bounds. And so on this graph, it's the plus and minus 2.48 standard deviations. First of all, you see the noisy data here, and the black line that you can barely pick up any of here is the best fit. And then the red dashed line is the best fit at 6 picomolar, which is the high level. And you can see it's still an excellent fit to the data. And the green dashed line is the best fit at 2.3 picomolar. The black line is best fit at 4.1, which was the average of those 3. So all these are really excellent fits. In fact, to the first significant digit, they agree. They're all 7% residual error. Now, if you go to multiple digits, these are lower. This is 6.98, and this one's 6.99. But they're very, very close. And visually, to me, no difference between these fits. All excellent fits. So I did a similar thing for KinExA. So the red dashed line here is at the 30-some picomolar. 33.2 picomolar. And that fit is definitely worse. And I can kind of believe that's a significantly worse fit. I can accept that. And so this is probably represents something that I shouldn't be saying. A fit this bad, I should reject that value of the KD. I'm comfortable with that. Now, on the low end, KinExA is telling me it can't resolve a KD. So what I did here was I went down to 10 femtomolar. And you can see here, there is a tiny bit of difference between the black line and the green line down here at this end. And the error is slightly higher. It's 7.2 versus 7.0. But that's still a pretty darn good fit. And I'm comfortable with saying that this is unresolved on the low end. This is a ratio of 32. This is a high curve, a high ratio curve. And high ratio curves are known not to be very sensitive to the KD. So I'm comfortable with this, and I'm not comfortable with this. And that, in a nutshell, is why I think that the scaled error approach is superior for KinExA data. Okay, how do we know these are reasonably accurate? Well, first, I've already described the simulations. There's, besides the one I showed you, there's a lot more of these. And they both methods work. There's 97% of the all fitted KDs in the KinExA CI compared to 96%. These are averages across all the noise and ratios. For the plus and minus 2.48 standard deviations. So that these both look good. These confidence intervals are approximations. We're trying for 95. And these are both totally acceptable approximations of 95 to me. And the second is through experiment. And I rounded up 131 experiments that all measured the same interaction. And these data were spread across multiple KinExA instruments by multiple different operators over a period of more than a year. But I had 131 of them all measuring the same thing. And this is real data, so I don't know what the actual KD is, but I assumed it was equal to the average of the 131. And then I counted how many of the 131 KinExA Pro confidence intervals included the average value, and the answer was 95%, 95.5%. I did the same thing. I went back to that data and I sampled it with 3 random points, and I did that 100 times, I think. And I looked at that, and again, 95%. So I strongly believe the asymmetric KinExA Pro confidence intervals are superior, and I always report them that way. But I acknowledge that if you want to do the extra work and measure your system several times and do a mean and standard deviation, in terms of a 95% confidence interval, it's likely to be okay. So in summary, the fact that your model fits your data doesn't mean it's the right model. If your reference gives you an activity greater than 100%, it's probably wrong and you should change your reference. Individual data points can be ignored, but you should justify your choice to do so. Drift correction and titrant-related NSB should not significantly change the KD or activity. If they do, you shouldn't use them. And also, please send me your data. I'd like to study it and see what I can learn from it. Use your SIG 100 levels with the sample volume and nominal concentration as a check for possible errors in CBP preparation. This is a pretty powerful tool. I use this a lot. As I say, I can normally do it in my head because it's not uncommon for you to cut your concentration by tenfold and increase your volume by tenfold, expecting the same SIG 100. That's a pretty common experimental strategy. And so if it deviates from that significantly, it's a flag to check and look into your concentrations. 95% confidence intervals are always estimates, but for KinExA data, I believe the error graph-based CI is a better estimate than the plus and minus 2.x standard deviation. And I believe this in spite of the fact that the 3-point standard deviations do appear and include the actual data 95% of the time. So be skeptical of your measurement data, be skeptical of your analysis. That's yours, that's mine, and everyone else's. Thank you.